Hello everyone. So in the previous lecture, we discussed about the liquid drop model, which explained the masses of the nuclei, the energetics of the beta decay and fission. But then we found that there are certain observations it could not explain, and they are essentially the fluctuations in the gross properties of the nucleus. So to explain those other phenomena which could not be explained by liquid drop model, another model has been proposed, and that is the nuclear shell model. So today we will discuss the nuclear shell model. Just to recapitulate, what are the limitations that the liquid drop model had, which it could not explain certain observations I have tried to list here. So the most important aspect that the liquid drop model could not explain was the extra stability associated with the magic number of protons and neutrons. In fact, what we discussed in the previous one, that if you draw the difference in the mass number and the mass, liquid drop mass and the experimental masses, then we found that the experimental masses are lower than the liquid drop masses for certain number of neutrons and protons, and this corresponds to, let us say, 2, 8, 20, 50, 82, and so on. So that means these nuclei have lower mass. That means they have higher binding energy, and therefore there is extra stability associated with this magic number. So this part could not be explained using the liquid drop. And associated with these magic numbers, there are other properties, other observations, like the very high suppression energy. Suppression energy means the energy required to remove a neutron or a proton for nuclei having this number of protons and neutrons. Again, the magic numbers, 50, 82, 126. So this is 126. Similarly, now if you have a nucleus having one neutron more or one proton more than the magic numbers, then that nucleus, that neutron or nucleon is very easy to remove. That means the suppression energy is very low for these nuclei which have magic number plus one nucleon axis. Again, associated with the magic number things. And also the nuclei having the magic number of neutrons and protons have, particularly magic number of neutrons, have very low neutron absorption cross sections, so that they, the next level is very high, so they are unable to, the probability of capturing a neutron become very small. Then again, if in the case of alpha decay, which we will discuss later on in the probably subsequent lectures, if the isotope has got 126 neutrons, that is again a magic number, then the alpha energy for such a nucleus is very low. Also, in fact, if after the alpha decay, the nucleus is having, the daughter product is having 126 neutrons, then the alpha energy is very high. So again, associated with the masses. Again, the magic number of neutrons and protons, they have very large number of isotopes. Particularly, if you have the 50 proton, so tin has got a large number of stable isotopes. Again, stability. Other than that, there are other observations like beta delayed neutron emission. Certain isotopes like fission products, 137 iodine, 87 bromine, these isotopes emit delayed neutrons, means they undergo beta minus decay, and after beta minus decay, the daughter product is left with an excited state that is more than the binding energy of neutron. So instead of gamma emission, that daughter excited state emits a neutron. They are called delayed neutrons because they follow the half-life of these precursors. Also, the isomers, the nuclear isomers are those excited states of nuclei which have a long half-life and they decay by gamma ray. Sometimes their decay by gamma ray is hindered. They can also emit beta minus or beta plus decays. So the nuclear isomers also could not be explained by the liquid drop model, and that is why there is urgent need to have another model that we call it the shell. So this is the cell model, which was proposed by Mayer and Jensen in 1949, and the shell model has certain assumptions, like here now it is more like atomic structure, no, where the nucleon, the electrons are revolving around the nucleus in a certain fixed orbits, stationary orbits. Here the nucleons move now, like in the atom, where we have a central potential offered by the nucleus is positively charged and the electrons are negatively charged, and electrons move around the nucleus because of the central potential, attractive potential of the nucleus. And so you have the assumptions about the stationary states of Niels Bohr. Here, in the case of nucleus, there is nothing like a central potentials, because the nucleons themselves constitute of the potential. So what is assumed that every nucleon moves inside the nucleus under the attractive potential generated by the remaining nucleons. So any nucleon you take, it is in a potential well that is formed by the other nucleons. Now, in the case of protons and neutrons, now they are in separate potential wells. So you start seeing two potential wells, one for neutron, one for protons. And like, for the atomic structure, you solve the Schrodinger equation for an electron. You find out the energy levels of electron, K, L, M, and shells. Similarly, in this case of nucleus, you will have which you solve the Schrodinger equation for the neutron and the proton in a particular potential well, you will get the energy states, and that energy states are analogous to that for the electrons. Now, as you know, these neutrons and protons are fermions, so they follow the Pauli exclusion principle, and so then you will find that in a particular state, only two nucleons will be occupying if they have to be paired up. So no two nucleons will have the same quantum numbers. So this is been followed, and in that way, when the neutrons and protons are orbiting in different orbitals, so essentially you assume this nuclear force is a weak force. In that sense, it is not a weak force associated with the beta decay, but it is compared to the strong force that we envisaged in the liquid drop model. In the shell model, the neutrons and protons are in separate potential wells, and they don't interact with the other nucleons in that potential. So in that sense, it is a relatively weak force. Okay. So essentially, though the cell model constitutes the solving a Schrodinger equation for the nucleon in a particular potential well. So what are the different types of potential wells that you can envisage? The simplest potential well is the square well potential. You have the attractive potential well having the depth of minus V0. This minus V0, so the potential well of the nucleus is of the order of 30-40 MeV deep potential well. And so the nucleus, when we are solving the equation, Schrodinger equation for a neutron or a proton, we assume this is the case, you can assume as a square well. So essentially you have Vr is equal to minus V0 up for r less than the nuclear radius, and then for more than r it is 0. So that is the typical attractive square well potential. So you can in fact solve the Schrodinger equation assuming a square well potential, or more realistically you can use as a harmonic oscillator. In the harmonic oscillator, again you have the attractive, the minus V0, the depth of the potential, and now it is a parabolic expression with r. So you have the potential minus V0 plus half m omega square r square, that is the energy of the oscillator. And so the frequency of this oscillator is nothing but k, the force constant upon the mass of the nucleon. So essentially the cell model will in the cell model we solve the Schrodinger equation for this harmonic oscillator potential, and then we get the energy, eigenstates, and the eigenvalue. Okay, so let us try to now generate the cell model scheme by solving the Schrodinger equation for a three-dimensional harmonic oscillator. So the potential for the harmonic oscillator can be given in terms of Vr equal to minus V0 plus the half m omega square r square, where omega is the oscillatory frequency that is given by the force constant upon the mass of the nucleon. And assuming that this oscillator is isotropic, that means the oscillation frequency in x, y, and z direction is same. Wx equal to Wy equal to W. So the Schrodinger equation for this will be H psi equal to E psi. We will not go into details of the solving Schrodinger equation. Our interest is to get the eigenvalues for this equation, and the eigenvalue of this Hamiltonian will be given in terms of the oscillator quantum number n plus 3 by 2 h cross omega. 3 by 2 is coming to the three-dimensional harmonic oscillator, and this is the unit of the oscillator energy. So the frequency of oscillation can be given by 2 V0 upon mr square, where r is the radius of the nucleus and n is the oscillator quantum number. And so the energy, the oscillator number can start from 0 to higher values, 0, 1, 2, 3, 4. And so as the n value increases, the energy of the cell increases. Now let us try to set up the eigenstates, the different cell model states. For that, like I told that the electrons are occupying the K, L, M cells in the atoms. Similarly, the nucleons, neutrons and protons are separately occupying the orbitals, like different orbitals like L, sp, df, and so on. And so there is a formula for the oscillator quantum number in terms of the different other quantum numbers. They are the n, small n, principal quantum number, and small l is the orbital quantum number. The principal quantum number n can take values 1, 2, 3, 4, and so on, whereas the orbital quantum number can take the value 0, 1, 2, 3, 4. And so corresponding to the value of L, we have S, P, D, F, G, and so on. So the different combinations of small n and small l can give you the same value of oscillator quantum number. And so you will find for the same oscillator quantum number, there will be multiple orbitals contributing to that particular oscillator quantum number, that we can see in the next one. So if you see let us try to now generate these cell model states for a harmonic oscillator. We'll try to fill the values of small n and small l, which will satisfy this condition starting from n equal to 0. So for 0 ground state of the oscillator, you can see here n small n equal to 0 and small l equal to 0. You can see here n equal to 1, 1 minus 1, 0 into 2, 0, and plus l equal to 0. So S way. So L equal to 0 means S orbital, and S orbital can occupy 2 nucleons. So the occupancy of this S orbital is 2, and the cumulative is also 2. For the next oscillator quantum number 1, again we can have, how can you get n equal to 1? So you start from small n equal to 1, 1 minus 1 equal to 0. So this term is 0. So we have L equal to 1. That is the p orbital. So capital N equal to 1 will have again one orbital p, and the occupancy of p is p6, 6 nucleons, and the total occupancy becomes 8. Now let's go to the next higher oscillator quantum number, n equal to 2. Here we can have now two possible combinations of small n and small l. You can see here, when you take n equal to 1, then 1 minus 1 is 0, and so you will have, when we have n equal to 1, so you can see here, okay, so here we are going to n equal to 2, so you will have n equal to 1 and 1 minus 1 0, so into 0, so L equal to 2. L equal to 2 is the D state, and it can occupy 10 nucleons, and in combination of that, so n equal to, now you can have n equal to 2, so 2 minus 1, 1 into 2, 2 plus 0. So you can have a 2s state. So basically you will have 2s, 1d, 1p, 1s. So you will have a 2s orbital close to the 1d orbital, which can take 2 nucleons, and the total occupancy becomes, you can see here, 6 plus 2 plus 10 plus 2, you will have 20 nucleons. Let's come to the higher oscillator compound number. So you can have small n equal to 1, 1 minus 1. So small n will take 1, 2, 3, 4 values. So 1 equal n equal to 1, 1 minus 1, 0. The system is 0, L equal to 3. So you will have 3f orbital, 1f orbital, and f orbital can take 14 nucleons. And in combination with that, you can have now n equal to 2. So you will have, and 2 minus 1 is 1, and 1 into 2, 2, 2 plus 1 is 3. So you have 2p orbital. And so these two, actually they are corresponding to same capital N, so their indices are very close. And then p can take 6 nucleons, so total is 14. Let's come to the n, capital N equal to 4. And here you can have now 3 combinations. N equal to, small n equal to 1, so L equal to 4. We have 1G, n equal to 2, and this L equal to 2, you have 2D, and n equal to 3, so you will have 3S. And so the occupancy of G orbital 18, D orbital 10, and you have 70. So you can see here that by filling the orbitals using this formula and their occupancy, you can see that we are not able to reproduce the magic numbers. Of 2, 8, up to 20, you can reproduce, but beyond that, the important magic number 50, 82, 126, we are not able to reproduce. So that means there is something missing in the cell model, which we have not taken into account. And so that is where the spin orbit coupling becomes important. You know, in the atoms, in chemistry, we have heard about the LS coupling. That means the small l orbital angular momentum of all electrons combined to give the capital L, that is the total orbital angular momentum, and the spins of all electrons combined to form the capital S, that is spin angular momentum, and the capital S and capital L combined, that is called the LS coupling or Russell-Saunders coupling, and that nicely explains the spins of the atoms. In the case of nuclei, because the spin orbit coupling is very strong, the L and S of the individual nucleons combine to form what is called the J, and so this is called the JJ coupling. That means the J angular momenta of each nucleon, they combine to form the total spin of the nucleus. So it is not the individual L and individual S. L and S coupled together to form a J. And so if you, in the potential for this harmonic oscillator, you take a LS angular spin orbit coupling term, that is minus UR L dot S, then you can, let us see how the level scale will change. So you can say the vector product of vector sum of the L and S will be J, and so you can write J square equal to L square plus S square plus 2 L dot S. And so L dot S, we want to get the magnitude of L dot S, J square minus L square minus S square by 2, and you can now write the magnitude of J square, L square, and S square of J plus 1, LL plus 1, and SS plus 1, that is half into 3 by 2. And so let us just see what happens to the spin orbit coupling. What does it do to the particular state? So we have now, instead of LS states, we have a J state. And so for J can be now L plus half, or J can be L minus half, right? So you have this spin, this L, it can be L plus half, or it can be L minus half, and so you will have different energy states. So each L state splits into 2 states, L plus half, L minus half. So when J equal to L plus half, then L dot S you can calculate from here, substitute J equal to L plus half, you get L plus half, L by 2. And so this L plus half state is, that means if you put L by 2 here, then this is a negative term minus U L dot S. So this is the lower energy state. And for J equal to L minus half, L dot S you put in this formula, you get minus L plus half by 2. So essentially meaning that L minus half state is raised, because if you add to put it here, the minus one will become plus, and so L minus half state is lowered. So the net result of spin orbit coupling is a particular L state. You have splitting of the L state, L plus half being lowered and L minus half being raised. The splitting between these two states is, you can calculate from here, L plus half by 2 minus of minus half, L minus L by 2. So that is L plus 1 by 2. So this is the gap between the two states. And so you can see here that as you go to higher and higher angular momentum values, orbital angular momentum values, the gap between the L plus half and L minus half is increasing. And this is what actually explains later on. You can see that the higher magic numbers, or the spin orbit because of spin orbit coupling, the higher cells are much more split, and that leads to rebunching of the orbitals in different cells. So that we will see in the next slide. So higher the L value, have the splitting, and that repercussion of that we will see in this particular. And now we'll fill the cell model states in the lieu of spin orbit coupling. So let us see how do we start filling the spin orbit coupled states. First thing is that we follow the Pauli exclusion principle. That means the nucleons. So no nucleons will have the same quantum numbers. That is the Pauli exclusion principle. But the main point is that when the filling of the electrons in the atoms and filling of nucleons in the nucleus is quite different. In the case of atoms, the maximum multiplicity prevails. The state having maximum unpaired electrons having lower energy. But in the case of nucleus, the moment you have two unpaired nucleons, they get paired up because the pairing energy is very high. Okay, so the L orbital, as we have seen previously, can accommodate 2 into L2 plus 1 nucleons like S2, P6, D10, F14, and so on. Accordingly, the occupancy of a J state, because L has been L plus half and L minus half, so each L has split into 2, and the total occupancy is equal to 2L plus 1 into 2. So the J states will have occupancy 2J plus 1. So 2J plus 1, every J state you will see 2J plus 1 occupancy. Then the pairing energy of nucleons is much more than the pairing energy of electrons. The electron pairing energy of the order of few electron volt, whereas in the case of nucleons, we have seen the delta value for pairing energy is 1 to 2 MeV. So it is a very high pairing energy. And the two nucleons of same type having same J are always paired up because of this high pairing energy, which is unlike the electrons in the atoms. So we will consider these facts while filling the orbitals by nucleons in the next slide. Now you can see here, so we have a J state which is arising from L plus half or L minus half, and occupancy of this is 2J plus 1. So this spin states, whatever I am showing, they are the J states of that particular orbit. So up to this we have already seen. So the S orbital is not split because L equal to 0, and so it occupies the two nucleons. The P orbital is split into 1p 3 by 2 and 1p half, and occupancy again 2J plus 1. So 3 by 2 is 4, 1 by 2 is 2. The D orbital will split into 1D 5 by 2, 1D 3 by 2, and S orbital is not splitting. And 5 by 2 will have 6, 3 by 2 will have 4, 1 by 2 will have 2. F orbital again will split into 2, 1s half and 1 5 by 2, and P orbital 2p half and 2p 3 by 2. So this is 1, 1, 1, 2, 1, 2, 1, 2, 3, so on. Okay, so these are the value of small n. So now you can see here G orbital will split into G9 by 2 and G7 by 2. D orbital will split into D5 by 2 and 3 by 2, and S will not split, and so on. H11 by 2, H9 by 2. Now you can see the occupancy. So what happens, whenever the F7 by 2 is lowered, this S, so up to 20 we have explained in the previous scheme. But now, in fact, this S will give you 28, and 28 also, there is a gap here. So this is called the semi-magic number, means 28 neutron, 28 protons also have extra stability, but this is not a complete magic number, but 28, the nickel, 28 proton, around 28 proton, there is a extra stability in the nucleus. So this is called a semi-magic number, but the major magic numbers at 50, again, because of the lowering of G9/2 level. So this G9/2 is a part of the lower level, lower shell. And so this bunching of these levels leads to what we call it the shell. So G9/2 lowered gives you 50, magic number 50. So that gives the stability. Similarly, H11/2, when it is lowered compared to H9/2, it explains the magic number 82. So this bunching of this H11/2 in the lower shell explains the magic number. So that is how, similarly, you will find I13/2 will give you 126. So the major factor responsible for reproducing the magic number is the spin orbit coupling, wherein the splitting of the J state, L state into J, L plus half and L minus half, with the L plus half being lowered significantly for high L value, that it is overlapping, it is close to the lower shell, and so the magic numbers can be reproduced. So this is now the up to scale. So you can see here the cell model states without spin orbit coupling 1s, 1p, 1d, 2s, 1f, 2p, 1g, and so on. And then you can now apply spin orbit coupling here. So as half 1p 3/2, 1p 3/2. Now, as you go to, so here till 20 there was no problem. You have now F7/2 being lowered. In fact, there is something called a semi-magic number of 28. So there is extra slight higher stability for 28 protons or neutrons. And now you see here, because of the lowering of 1G9/2, there are no additional 10 nucleons here. So there is a 50 nucleon shell magic number. And again, lowering of the H11/2, you get 82. Lowering of the I13/2, you get 126, and so on. So you can see, and the gap, this, because of the gap between the L plus half and L minus half states, for higher L values, the differences are rising. And because of that, we are able to explain the magic numbers of the nuclei. So the orbitals that are responsible for these magic numbers are the L plus half state of D, F, G, H, and I. So this is how you can see that L plus half state gets lowered, and then it bunches with the previous shell, and so you get the magic number of. So this is what the cell model explains, and the other aspects, how we can apply the cell model in predicting the different properties that we could not use in the liquid drop model, I will discuss in the next part of my lecture. So I will stop here and take up the applications of cell model in the. Thank you.